faster than the space-time fabric can. If you don't keep up, it will just tear me apart. Terrified by this at this moment in our night, the sky is rapidly changing, and in just a matter of years, if not decades, it may disappear completely from sight. Around the world, astronomers are sounding the alarm. Experts like deGrasse Tyson have recently announced that Polaris's explosion and the tail behind it are quite frightening. Polaris, known as the North Star, remained constant in the night sky long ago, serving as an important point of reference for astronomers and navigators. However, this might alter our night sky in the near future, and measurements made by the stars may change forever. Let's investigate the significance of this threat and its implications for each of us as we uncover the story of Polaris as it approaches its end. For centuries, Polaris has guided astronomers and mariners alike, holding a revered position as a guiding light. Its unwavering presence in the night sky has been essential for navigation, but that stability may soon be altered. In September 2023, a research paper presented by the esteemed Royal Astronomical Society cast out the fate of this celestial luminary. Polaris is on the brink of exploding, facing possible disappearance from the night sky forever. Before we explore the repercussions of this revelation, let's learn more about Polaris. Known as the North Star or Pole Star, Polaris is unique because it is close to the celestial North Pole, situated almost directly above Earth's North Pole. It appears nearly stationary in the northern sky within the constellation Ursa Minor, or the Little Dipper. Polaris shines as a moderately bright yellow-white supergiant star, which is much bigger and brighter than our Sun. It is not a single star, but part of a complex system of 3 stars, with Polaris A and B forming a binary pair, while Polaris B orbits around them. The interactions between these stars result in gravitational forces that shape their behavior and orbits. Any disruptions in these interactions can result in erratic variations in the star's brightness or pulsation patterns, but the specific mechanisms behind these interactions remain unclear. Polaris is located approximately 323 light-years from Earth, which means the light we see today began its journey over 3 centuries ago. Thus, if Polaris exploded now, we wouldn't observe it until over 3 centuries later. It's even possible that Polaris has already exploded, and we're yet to witness the light from that event. Throughout history, the North Star has held immense cultural, navigational, and symbolic significance due to its stability. Its fixed position was a tremendous help for ancient navigators, guiding them across seas and lands. Symbolically, Polaris stood for permanence and guidance, remaining steadfast amidst the ever-evolving night sky. For astronomers, Polaris served as a crucial reference point that aided in the study of space, time, and variable stars. As a variable star, its periodic variations in brightness have provided valuable information about stellar properties and the nature of variable stars. This characteristic also played a pivotal role in determining cosmic distances and calibrating instruments. These pulsations follow a predictable pattern that has been the standard for stars, making it easy for us to anticipate its behavior. However, recently, Polaris has strayed from this expected behavior. This irregularity in its pulsation cycle has puzzled astronomers, leading to a closer look at this celestial anomaly. Instead of its usual predictable pattern, Polaris has started to show erratic cycles of dimming and brightening. Scientists are now raising concerns that the star may be nearing the end of its lifespan. This corresponds to the typical actions observed in stars that are about to die. The gradual lengthening of Polaris's pulsation period, which was once stable, is attributed to interactions within its star system. We have observed a yearly rise in the 4.5-second period of pulsation, which, despite its insignificance, holds significant implications. Some astronomers have hypothesized that gravitational interactions between the Polaris stars could be responsible for these shifts in its atmospheric conditions, directly affecting the patterns of its pulsations. However, others are more worried, because they believe the star is on the brink of exploding. The similarities that exist between Polaris's behavior and that of Betelgeuse, another important star in the constellation Orion, are striking. Both stars have shown baffling inconsistencies in their luminosity, posing questions regarding their potential for explosions. Stars in their twilight stage often exhibit such irregularities before reaching the culmination of their life cycles. NASA has expressed heightened concern about Betelgeuse, but not the same amount of attention has been explicitly targeted at Polaris yet. As a star nears the end of its life cycle, it progresses through various phases, including the main sequence phase, the red giant phase, and, ultimately, the supernova explosion. Based on Polaris's erratic pulsations, scientists believe it has reached the helium-burning stage, typical of stars nearing their depletion. These irregularities in Polaris's behavior align with patterns indicative of stars in their twilight phases, but definitive indications of its nearing supernova remain inconclusive. Astronomers are focusing their attention on these anomalies to comprehend what would happen to Polaris if it went supernova, which would probably be a spectacular event in our sky, potentially outshining the moon. It could become one of the brightest objects visible for days, weeks, or even months. Its appearance could significantly alter, temporarily transforming how we view familiar constellations like the Big Dipper or Ursa Minor, which includes Polaris. You can rest assured that Earth is most likely perfectly safe, even if Polaris were to explode because of its size and distance from us. Whereas an explosion caused by Polaris might be as visually spectacular as that of Betelgeuse, it might still be visible to the naked eye for an extended period and surpass astronomers who study nearby stars. An observer would undoubtedly pay attention, igniting curiosity within the scientific community and among stargazers worldwide. However, the particular visibility and impact on Earth's atmosphere or surroundings would be less significant compared to a closer supernova event. But what will Polaris itself be like? To clarify one thing, while giant stars typically end their lives with a supernova, this is unlikely to be the case with Polaris. When a massive star goes supernova, a massive explosion occurs, indicating the final cataclysmic phase of its existence. This process results in the total collapse of the core, causing a severe shockwave that sets off the star's explosion violently. But Polaris is not massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers before becoming a white dwarf. This transformation won't result in a supernova, but rather a peaceful end as it develops into a very small, dense stellar remnant. A white dwarf is the remnant of a low or medium-mass star that has used up all of its nuclear fuel. It is extremely dense, roughly the same mass as the Sun but compressed to Earth's size. As a result of this, we will no longer be able to observe its remains on Earth, similar to how we look at the star today. Comparing the expected outcomes of Polaris's end with historical occurrences of supernovae provides useful knowledge of the formation of stars and their final fates. Compared to our expectations, clearly documented supernovae like SN 1987A and more recent events like SN 2014J or SN 2011Phi offer valuable insights. Polaris provides useful information for understanding the possible consequences of its burst. For example, SN 1354 produced the Crab Nebula's formation, a nebula that continues to expand and emit radiation with a variety of wavelengths, providing astronomers with a wide range of data. Similarly, studying SN 1987A, observed in the Large Magellanic Cloud, provided insights into the processes of nucleosynthesis and the dynamics of supernova remnants. Analyzing phenomena such as how nebulae are formed, the variations in the amount of cosmic rays released, and insights gained from luminance reveals unique characteristics of Polaris. The formation of nebulae, like the Crab Nebula, results from the expulsion of material during a supernova explosion, which interacts with surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the cycle of stellar birth and death. In addition, The emission of high-energy cosmic ray particles, accelerated by the shock waves of a supernova, has implications for astrophysical processes and radiation in space environments. To arrive at a final comparison, scientists evaluate differences in the composition, mass, and speed of ejected materials between an anticipated Polaris burst and other observed events. This necessitates investigating the spectra and remnants, light curves from these events, and projecting similar characteristics for the expected Polaris burst, determining whether it might lead to the formation of distinct nebulae or influence the distribution of elements. This enhances our understanding of its potential outcomes. Another crucial area of investigation includes assessing pulsational stars with decreasing variability, like Polaris, which were once observed as precursors of supernovae. This comparative analysis can help gauge similarities or deviations and provide insights into the mechanism of the burst. Pulsational variation in nearby stars, whose passing may serve as an example of instability or imminent catastrophic events, offers clues to the processes of evolution that lead to supernova explosions. Despite meticulous observations and in-depth research, astronomers are left perplexed by the irregularities observed in Polaris's behavior. Revealing the individual factors causing these irregularities holds the key to advancing our comprehension of stellar evolution. Understanding the mechanisms responsible for Polaris's irregular pulsations requires collaboration across disciplines and the development of sophisticated observational and theoretical models. The possible loss of Polaris as a crucial point of reference in the night sky poses substantial concerns for astronomical endeavors. Ground-based telescopes and celestial measurements would necessitate a new calibration, affecting the precision of astronomical calculations. The absence of Polaris could also impact navigation systems and cultural practices based on stars and planets, highlighting the significance of this celestial event. The enigmatic behavior exhibited by Polaris emphasizes the necessity for deeper investigations and dedicated efforts by astronomers. Researchers must grapple with the complexities surrounding its erratic pulsations and provide specific responses while acknowledging the significance of progressing our comprehension of the complexities of space-time. Ultimately, the answer to Polaris's fate remains uncertain, and only time will reveal its true nature. Nonetheless, the pursuit of understanding and knowledge, despite cosmic unpredictability, is a testament to humanity's enduring curiosity and efforts to decipher the mysteries of the universe. The implications of Polaris's potential transformation extend beyond the purely astronomical. They touch on the very fabric of how humanity understands its place in the cosmos. Throughout history, celestial bodies have recorded time and guided navigation, directing explorers through uncharted waters and lands. The loss of Polaris would not only disrupt traditional methods of navigation, but could also have far-reaching effects on cultural mythology and symbolism tied to the North Star in various cultures. Folklore and spirituality, for example, rely heavily on Polaris. Native American tribes often viewed Polaris as a light of direction in their stories, illustrating perseverance and hope. Similarly, the North Star was utilized by ancient Egyptians in their architectural designs, aligning the position of the pyramids with the sky. The disappearance of such a pivotal star could alter cultural narratives and the human experience as a whole in relation to orientation. In addition to navigation, the scientific community stands to face significant challenges if Polaris were to disappear. Astronomical observations heavily rely on established reference points. Polaris's role as a constant has facilitated the calibration of instruments and models used to study distant galaxies, star structures, and even the expansion of the universe. If Polaris suddenly vanished, many of these systems would require recalibration, possibly leading to inaccurate measurements and misunderstandings of cosmic phenomena. As astronomers shift their focus to observing Polaris with greater attention, new observational technologies are being developed. Advancements in spectroscopy and photometry allow scientists to analyze light emitted by stars in unprecedented detail. These tools help in detecting minute changes in brightness, which are necessary for comprehending the mechanisms driving stellar behavior. As researchers hope to collect more data to improve their stellar models, stars in the later stages of their life cycles, particularly Cepheids and red giants, could be very helpful. For example, astronomers observe variables like the relationship between brightness and time, which aids in measuring distances across the universe. By comparing these stars' behaviors to those of Polaris, scientists hope to gain a clearer understanding of stellar dynamics and evolution, enriching their comprehension of our galaxy's architecture. Moreover, as the search for exoplanets accelerates, Polaris and its companions become more significant. Understanding the characteristics of stars in triple systems can provide crucial insights into the development and adaptability of planets orbiting them. Astronomers are keenly interested in how such stars influence their environment, affecting the conditions under which planets form and develop. If Polaris experiences a significant event, such as a pulsation leading to its transformation, it might serve as a natural laboratory for studying stellar life cycles. Occurrences like these would not only provide a window into stellar death, but could also illuminate aspects of nucleosynthesis, the process by which stars create elements. Polaris's remnants may contribute to the interstellar medium, enriching it with heavy components necessary for the creation of new planets and stars.